We begin with the problem. Now I'm just going to quickly kind of work through one problem to give you the flavor of how we obtain solutions. Then we talk a little bit about some of the theory, some of the things you need to know in order to do this, which hopefully you do know, but at least I can define what you need to know so that you can do these operations. So without further ado, let's just consider the following problem. We have two differential equations in y1 and y2, where y1 and y2 are functions of t. First equation says that y1 prime equals 5y1 plus 2y2. Second equation says y2 prime equals 4y1 plus 3y2. I didn't really need to read that to you, but I did. Okay, we want to find functions y1 of t and y2 of t that satisfy this system. Now, why would we want to do this? Well, we'll motivate this after we look at the procedures. Let's just kind of get an idea of what we're going to need to solve this type of problem. Then we'll talk about where they can come from, where problems of this nature can come from, and again, what you need to know in order to actually do the solutions of these problems. The first thing we do with an equation of this form is represent the equation as a matrix, rather the system as a matrix equation. Now that's something you should be familiar with from solving simultaneous equations in algebra class. So to represent this as a matrix equation, I'm going to just pause the camera here and write down the matrix equation that corresponds to this. Now I've started to write out the matrix equation. y1 and y2 are the functions, these symbols we have on the right hand side, y1 prime y2 on the left hand side. We want a matrix that we can multiply by the column vector y1 y2 to get the column vector y1 prime y2 prime. What matrix would go here? Well, when we do matrix multiplication, and of course matrix multiplication is one of the things you need to know, so make sure we put a little note here. Know how to do matrix multiplication. With an exclamation point or two or three. Now, if I write two numbers in a row here, they'll multiply the two numbers in a column. And if I write the numbers 5, 2 here, well, 5 times y1, 2 times y2. If I add 5 times y1 to 2 times y2, which is exactly what it means to multiply this row by this column, I get this expression up here. So the 5, 2 takes care of this part of the equation, because then the first row multiplied by this column has to equal the first row of this matrix, which is y1 prime. So already we have y1 prime equals 5y1 plus 2y2, the first equation. Second equation we can write very similarly, 4, 3. 4 times y1 plus 3 times y2. It's the second column, second row times the column is going to equal the second column of, or the second row of this matrix. So this matrix product represents our matrix equation. The next thing we do, and at this point you probably have no idea why we would do this, but it's kind of analogous. It is analogous to what we did with second order constant coefficient equations. Assume a solution of the form e to the lambda t. Now e to the lambda t is not going to be a solution, because e to the lambda t, or a multiple of e to the lambda t, would be only a single function, and our solution has to consist of two functions. But we're going to assume a solution that's based on the idea that the derivative of e to the lambda t is a multiple of e to the lambda t. The other thing we need for this solution is we need two components. So we'll call the components x1, x2. Now if this is multiplied out, we get e to the lambda t times x1, e to the lambda t times x2. This is going to represent a y1 and a y2 function that will hopefully solve the equation. our task is to find a value of lambda and a value of x1 and a value of x2 to satisfy our equation. And that's our matrix equation that we're trying to satisfy. And I didn't really leave myself enough space to write this, but I'm going to do it anyway. This is a y1, y2, which is equal to e to the lambda t. That is, we're assuming this column here is of this form. Now, we know what this column is, so we could already fill in e to the lambda t times x1, x2 over here. What's the derivative of this function going to look like? Well, x1 and x2 are constants. x1 and x2 and lambda are going to be constants. We're going to make that assumption. So that if y1, y2, write it out a little better here, equals e to the lambda t times x1, x2, then y1, y2 prime, which is just y1 prime, y2 prime. Now we haven't defined the derivative of a column vector, but the definition is just as obvious as you might hope. The derivative of this column is what we get if we take the derivatives of the functions in the column. Well, anyhow, the derivative of that is just going to be lambda e to the lambda t times x1, x2. x1, x2 being a constant vector, so that it has the derivative of the x1, x2 vector is 0, so that by the product rule we get this expression for the derivative y1 prime, y2 prime. Now our matrix equation becomes 5, 2, 4, 3 multiplied by e to the lambda t times x1, x2 equals lambda e to the lambda t multiplied by x1, x2. Without, at this point, going through the details, which you would be familiar with if you've had a linear algebra course or any kind of matrix algebra, this e to the lambda t is a function of t, but it's just, for any value of t, just a number, and we can actually factor it out of this product, and we can factor it out of this product, and then just being a number, we can divide both sides by that number, which is just going to get rid of our e to the lambda t. So that our equation becomes 5, 2, 4, 3 multiplied by x1, x2 equals lambda multiplied by the x1, x2 vector. Okay, sorry if the shift in pages is a little bit shocking, but I've gone ahead and written out an equivalent equation here. And the reason this equation is equivalent to this is simply that if I multiply the matrix 1, 0, 0, 1, which is called our identity matrix, so we call that the identity matrix, which we call I, and I call that I sub 2 because it's a 2 by 2 identity matrix, 2 rows, 2 columns. If you understand matrix multiplication, 1, 0 multiplied by the column x1, x2 gives us x1. So that if I multiply this matrix out, the first row of the product matrix will just be the x1 that we had before. And the same thing for the second, or the analogous thing for the second. 0, 1 times x1, x2 is just x2. So that I haven't really changed anything by making this substitution. But now I'm going to use a little bit of matrix algebra, a couple of simple and straightforward properties of matrices you might not be familiar with, but they should make some sort of sense. Now this step reads just pretty much like this step, except that what I've done is I've multiplied lambda by the numbers in this matrix, so that lambda times 1 is lambda, lambda times 0 is 0, and lambda times 0 is 0, lambda times 1 is lambda. I've also used an associative law, and again, we haven't proved this associative law, but if I have a product like this, where the this matrix is multiplied by this column vector or matrix, multiplied by a constant out here, I can group the constant times the matrix, again, by an associative law, and then a constant times the matrix just multiplies the constant times everything in the matrix. I added 2 more steps while you weren't looking. Here I've simply subtracted the right-hand side from both sides of the equation to get this equation with 0 on the right-hand side. That should be very straightforward. And then I've used another property of matrix multiplication, that if one matrix times x1, x2 plus or minus another matrix times x1, x2 will be equal to the sum or difference of those two matrices multiplied by x1, x2. And this is just the linearity of matrix multiplication, very much analogous to this linearity we have for differential operators and in just straightforward algebra. Next, I simply subtract this matrix from this matrix. So 5 minus lambda gives me 5 minus lambda, 2 minus 0 gives me 2, 4 minus 0 gives me 4, 3 minus lambda gives me 3 minus lambda. And I now have a matrix multiplication, a matrix equation for x1 and x2. Now this equation has 3 unknowns. It has lambda as an unknown, it has x1 and x2 as an unknown. This is really 2 equations. The first equation, if I multiply this row by this column, gives me an equation for x1, x2. And if I multiply this by x1, x2, I get another equation for x1, x2, setting this times this equal to 0 and this times this equal to 0. Now, I was being a little sloppy. I wrote down 0 over here. If I'd have put an arrow over the top of it to make it a vector, I could have gotten away with it. But it's really the column matrix 0, 0, because, of course, every one of these equations stands for 2 linear equations, just like this matrix equation here stood for these 2 linear equations. Each linear equation has to have a right-hand side, so we have to have the 2 zeros here. So we have 2 equations, but we have 3 unknowns. So what are we going to do about that? We'll see that in the next clip.